Yeah, Pranav, you can start discussing.
Okay, so before you attend the talk, I'll talk about a few important things. Firstly, we have started a mailing list where you can give your alternate emails and we can give you about reminders and major updates on the website. I don't like spam as much as the next guy, so we'll make sure you aren't getting spammed or anything. Secondly, we are starting a weekly problem set that will be posted today at 4 p.m. We intend to repeat the same every week. I mean, we intend to post a new problem set every week. Also, you can suggest questions or comments about future problem sets on the website. Also, these are problem sets of the week and not problem sets of the hour or month. So if you feel it is too easy or too difficult, please let us know. Thank you.
All right, so we can start with the talk. So basically, this is a continuation of yesterday's talk on arborealism in group theory by Balarka Sen. So yeah, let's start.
Yeah. So, all right. So shall I start?
Yeah.
Okay, thanks. Never really too sure. Okay. So yeah, this is the second half of my talk. So basically, the outline today is okay. Great, everything's working. So so some recall. Then we move on to talk about um, property FA, which is about, so F stands for fixed point and A stands for action. So we're going to talk about actions of groups on trees with fixed points. And then property T from there. I'm not sure how much I'll be able to talk about property T. And so this is something I would like to talk about, but not sure if I'll have the time. So this is something about p-add x and local fields. Oops. Yeah. 5. Something about Bruhat-Tits trees. Okay. So this is basically what I want to do for today. So let's see. Last time we proved the following theorem. If G is a group acting without inversions on a tree X, on a graph X, the fundamental domain being a segment, then edge joining two vertices P and Q. Then the following are equivalent. X is a tree and G is an amalgamated product of GP and GQ. GP and GQ being the stabilizers of P and Q. And GE is the stabilizer of the edge. Yeah. So, right. And the theorem also has a converse. So let me just mention the converse before I sort of go through the argument once again for someone. I mean, yeah, someone I think asked me to go through the argument again. I'll just sketch the argument once again. So the converse is that if G is in fact amalgamated product, G1 star A G2. Yeah. Yeah. Then there is an action of, then there exists a tree such that G acts on the tree, fundamental domain with fundamental domain, a segment such that GP equal to G1, GQ equal to G2, and GE equal to and GE equal to, one second. A, yeah. So yeah, so what is the idea behind this theorem? So let me just recall briefly. Oh, if you go to the next page and add a page insert. Yeah, okay. So one second. How do I add a page after this one? Yeah, that's it. So let's see. The idea was we proved so yeah, so there is a map phi from, so we're proving a theorem here, right? Not the converse. I'll show you how to prove the converse as well. It's not hard. So there is a map phi from GP star GQ along GE to G. So what is the map? GP and GQ are stabilizers of P and Q, right? So there are inclusion maps from GP to G and GQ to G. So there is a inclusion. So what is how does map come about? So there are inclusion maps from GP to G and GQ to G. Yeah. And there is and GE is really the intersection of GP and GQ. Yes. So therefore we get a map from GP star GQ along GE to G just by sending a word on the generators of GP and generators of GQ to the corresponding element of G. Right? So we get a map like this, and we have to show that this map is both surjective and injective. So to prove it was surjective, we showed that G is generated by GQ and GP and GQ. And that was basically because the graph X is connected. So this is implied by the fact that X is connected. Okay. And the fact that it is injective was implied by the fact that X has no circuits. It's a tree. Okay.
Oh, okay, got it. Thanks.
Yeah. All right. Okay, so that was the idea. And for the converse, yeah, so the converse is really easy. So suppose we already have that, the converse, suppose we already have that G is equal to G1 star A G2. So this might make it more clear. I mean, why exactly this is an amalgamated product. You look at G by G1, the coset, the set of all cosets, okay? G1 is, of course, cannot be a normal subgroup of G. It never will be, in fact. Look at the cosets of G1 in G, and look at the cosets of G2 in G. Yeah. Think of it as a set, and look at the disjoint union of these two sets. I'll define a graph whose vertex set is exactly this. And edge set is defined as follows. Edge set is, yeah, exactly G by A. What are the structure maps? Remember, our graphs were equipped with structure maps, right? It had an endpoint map and a conjugation map. Okay, so to get the conjugation maps, I should set it to be, yeah, I should set the edge set to be G by A, all elements of G by A, and their conjugates, formal conjugates, right? This is symbol. I mean, you can think of every element of G by A as a symbol and take the conjugate symbols. And so what are S and T? The starting point and the ending point. Well, just note that there for any, so just know that there are canonical maps from G by A to G by G1, G by A to G by G2, right? Because A is a subgroup of G1 and G2. So there are inclusion maps from G1, A to G1, A to G2, right? And this gives a surjective map from G by A to G by G1, G by A to G by G2. And these are exactly S and T. This is S, this is S, and this is T. And the conjugation map from E to itself is just taking a symbol and taking it to conjugate. So if the symbol belongs to G by A, take it to its conjugate in G by A bar, and conversely. Okay. So is this construction clear? How to get this graph? So of course this graph is a tree, right? This graph gamma is a tree. Well, why is it a tree? You need to justify. That's because yeah. That's because of the fact that if you have a yeah, if you have circuits here, then they would correspond to words in G1 star G2 along A, which are of the form yeah. So if you have a circuit here, so let's see. Gamma circuit gives rise to an element of a word of the form W1, W2, dot, 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 Wn equal to identity in G1 star G2 along A, where none of them consecutively belong to the same, yeah, what do I want to say here? One second. Yeah, so none of them, so if Wi belongs to G2, then Wi plus 1 will belong to G1. Consecutive elements do not belong to the same thing, because that's what happens to edges, right? I mean, when are there two edges between two vertices? They have to belong to different, because S maps to G by G1 and T maps to G by G2, right? So the endpoints have to belong to different classes. So this gamma is really bipartite, right? So if W1 belongs to G1, W2 has to belong to G2, and the word is of this form only. But such a word cannot be identity in a free product, because we discussed that last time. You need to prove it, of course, but that is true. So is this construction clear? Is construction of gamma clear? If it's not clear, just let me know. Also, you're able to hear me, right? There are no, I mean, interruptions. Right?
Yeah.
Okay, great. Because I think once it showed me that my internet was unstable. I'm never really too sure. All right, so this gamma is a tree, and G acts on gamma. Obviously, right? Because it acts on all these cosets. And what is the quotient? The quotient is exactly it's a segment, right? Because it's a bipartite tree, and G is acting transitively on this bipartite tree. So by transitively on a bipartite tree, I mean that it acts transitively on all the blue vertices and all the red vertices. Yeah. And the quotient has to be an edge between the blue and the red vertex. So this tree has so if you look at gamma by G, so if you look at gamma by G, this will be a segment. This corresponds to a vertex. This corresponds to a coset of G1. So let's say just G1. This corresponds to a coset of G2, just G2, the identity coset. And this corresponds to an element of G by A, just A. Yeah, this is exactly what it corresponds. This is exactly the quotient. All right. So I hope this construction is clear. So there's a one-to-one correspondence between groups acting without inversions on a graph with fundamental domain this. And what this really means is that it's a bipartite graph, and groups which are amalgamated products. That's the gist of it all. Okay, so what if the fundamental domain is not a segment, right? G is acting on a graph, let's say tree, I don't care. G is acting on a tree without inversions. What if X by G is not a segment? Yeah, it can be something, right? It can be a tree, right? Or it can be something different. I mean, it can be a general graph. What then? I mean, our theorem does not apply. Well, you can have a generalization of this theorem. So to introduce that, so let's study what X by G has to be. So look at X by G. Say X is a general graph. Let's say here, X is a general graph, and you look at quotient of X by G under some action without inversions. Then X by G is some arbitrary graph. It can be anything. It can have loops, multiple, I mean, you can have loops, yeah, multiple edges also. It may not be a combinatorial graph at all. So, but it has more data associated with it. So we can try to recreate something similar to what we did for fundamental domain and edge. So for every vertex of x by g, you have associated to it the stabilizer of that vertex, right? Of a lift of that vertex in x, right? So every vertex in x by g comes from a bunch of vertices in x, right? All in the same g orbit. And all of those in the same g orbit have the same have isomorphic stabilizers. They're all conjugate, right? Stabilizers of points in the same orbit are all conjugate. So they're in particular isomorphic. So for every vertex in x by g, you have some isomorphism type of some group, right? So GV. This is the isomorphism type of the stabilizer. And for every edge, you also have the stabilizer, isomorphism type of the stabilizer of that edge or the lift of that edge in x. So this is what a graph of groups is. You have a graph and you have to each edge, associated to each edge, you have some group. And associated to each vertex, you have some group. And also there are inclusion maps from edges to edge groups to vertex groups. Yeah. So that is what a graph of group is. So a graph of groups is more precisely a graph gamma with vertex groups, edge groups, and inclusion maps from, okay, but inclusion maps, yeah. And inclusion maps from edges to vertices. Yeah, maybe I won't put that in the data. Yeah, so gamma is a graph, gamma V vertex groups, gamma E edge groups, and gamma E includes in gamma SE, gamma E includes in gamma TE. Okay, that is what a graph of groups is. So x by g, it's a quotient of a graph. A quotient of a graph under the action of a group without inversions gives you a graph of groups. The quotient graph of groups. So maybe I'll denote the quotient graph of groups as x by g square brackets. Yeah. Or yeah, maybe let's denote it as x double quotient g. Just to denote it as, I mean, something which is not a graph. It's not just a graph, right? It's a graph with all these data. So I'll denote it by x double g, double quotient g. Yeah. Yeah. So yeah. So here is another notion. So to introduce that, I should introduce a new page. So here is another notion, which is fundamental group of a graph of groups. So suppose you have a graph of groups, gamma V, gamma E is a graph of groups. You can look at this following group, which is the, yeah, just one second. Yeah, so look at the following group. I shouldn't use F. We have already used F before. So how do I denote it? Let's say script G. Denote by script G to be the wage of all the vertex groups, V varying over all vertices of gamma, on the edges, E varying over all the edges. I should write it here. E varying over all the edges. Okay. So this is So this is basically, I'm taking weight of all the vertex groups, and for each edge, I'm taking the free group on the edges of the graph. Yeah, free group on just the edges. Yeah, generating set being just the edges. And look at the, yeah, okay, so this is one thing. Now if you choose a tree, choose a maximal tree T of gamma, then there is a natural subgroup, then there is a subgroup which is, script H is hard to write, which is generated by let's see, so basically the picture for this one is you take, say, any graph of groups, and you're taking weight of all of these things, GV1, GV2, GV3, and free group, and you're throwing in some new generators for each edge, right? E1, E12, E23, E13. Okay. Now, after choosing a maximal tree, I'm saying you have the following subgroup, which is generated by the free group on, yeah, so I should just say it like this, generated by all the edges in the tree, so if you choose an maximal tree here, are quotient by all those edges, and yeah, so one second, trying to find the right notation, E such that E is in T, and yeah, E T yeah, E alpha E inverse, one second, yeah, and okay, also E and E bar should be E bar should be inverse of E. E bar being the edge in the other direction. Okay, I'm also quotienting by that. And E alpha E bar is equal to so E T alpha. Yeah. E T alpha E bar is equal to S alpha. Okay, for all E which are not in. So these are for the edges which are not in the tree. E not in T. E not in T. Yeah. So in this special case, triangle case, we have a maximal tree, which is just the yellow tree, right? So here what we do, we take GV1 star, GV2 star, GV3 star, free group on these three things, three edges, right? Which is F3, let's say. And then we quotient by E12, E13, and also this weird relation, right? E23, so I have no space. E23 S alpha, sorry, T alpha, alpha being alpha from, so I should also write that here, alpha from GE23, yeah. E23, so GE, not 23 here, GE here, just here. E23 T alpha E23 bar equal to S alpha, where alpha is in E23, GE23. So this is the subgroup corresponding to any tree. Then the fundamental group of the graph of groups at this tree, chosen tree, which, okay, so I should get a new page. So then the fundamental group of this graph of groups, gamma, at the chosen tree, T, is defined to be this capital G by capital H. H depends on T. Just note that H depends on T. So I should write that here. And why is this called fundamental group? So there is a reason for that. The reason is that it is a fundamental group of something natural. So you can take, so again, for people who know algebraic topology, you can take, so for a graph of groups, you can take so you have this edge groups associated to it, right? So G12, let's say, just call it G12, G23, G13. You can take the classifying space of everything. You can take B here. You can take B of everything. And then take a co-limit and take them, take mapping cylinders for every edge, take classify, and then attach it to the vertex groups, vertex spaces. And then once you take fundamental group, you get back this pi1 gamma t. So that's why it's called the fundamental group of the graph of groups. The choice of the tree is just so that you can collapse. Yeah. Basically, if you collapse these edges, what do you get? You get a loop, right? So suffices to take graph of group of this loop. And for a loop, the fundamental group is just the H and extension. I'll define it right now. But for those who already know the story, it's the H and extension. So that's why these kind of relations are there. So let me do it for two examples. So two examples here are, we have seen these kind of graph of groups, which are just an edge with stabilizers of vertices, stabilizers of two vertices attached to two of the vertices, and stabilizer of the edge attached to the edge, right? So then what is the graph of groups? Well, you can just compute it. Yeah, one sec. So the graph of groups should be the amalgam. But why? So I've defined it after choosing a tree, choosing a maximal tree. But then I think there is some issue. Yeah, okay. The issue is that I shouldn't write this here. The issue is simply that I shouldn't write this here. Just write this alpha in. And not even this one. So let's see. Then what is this amalgam? You can write, it's just GP star GQ star the free group on one thing, so which is just a cyclic group. Quotient by, choose this. So there is a unique maximal tree here, so which is just this edge, right? You're quotienting by what? You're quotienting by E, and E S alpha E bar equal to T alpha, maybe the other way around, but it doesn't matter actually. E T alpha E bar equal to S alpha E bar equal to 1. Yeah, but you're already quotienting by E, so this goes away, clearing the numerator and denominator. And then after E goes away, these two things also go away. So what you have is here GP star GQ by S alpha equal to T alpha for all alpha in GE, right? And that's exactly the amalgam. Is this example clear? Just tell me if it's not clear. Or some brave soul can just tell me if it's clear.
Yeah, kind of.
Okay, great, thanks. And what you can do is you can also, so this is another example. You can also define graph of groups for this. So this is an edge with one vertex, right? So it's a loop with a single vertex, and you have GP here and GE here. So what is the graph of groups for this guy? Well, let's see. There is no maximal tree here, just maximal tree is just one vertex. So what you get is GP star, a copy of Z corresponding to the edge. And you're quotienting by what? You're not quotienting by the edge anymore because the maximal tree does not have any edge. There is unique maximal tree. After choosing the maximal tree, you see that there is no edge. So you're quotienting by E bar equal to 1, E T alpha E bar equal to S alpha for all alpha in GE. Yeah. And that is exact. So you can write down a presentation for it. So what is happening here exactly? Just forget this E bar equal to 1. Yeah. Just E bar is E inverse. That's all it's saying. So what you're saying here is you're taking this free product with Z and then you're quotienting by E alpha E inverse equal to E S alpha E inverse. Yeah. E S alpha inverse T alpha, sorry. E T alpha E inverse equal to S alpha. It doesn't matter, but just to be precise. Okay. So what is happening here? So what's happening here is that you have a single group, which is GP, and you have some subgroup, which is image of S. So image of GE under the map S, under the map S, yeah. So this is SG, yeah. This is some copy of G, and you also have another copy of G here, which is TG, right? And then you're gluing these things. Right? So it is self-gluing a copy of. So you have two isomorphic copies of a subgroup inside. So you have two isomorphic copy of a group inside the group main group GP, and then you're gluing it back to itself so that you get that these two copies are conjugate in the new group. And this is called an HNN extension. The HNN here stands for Higman, Neumann, Neumann. I don't know how these two Neumanns are related. Yeah, I'm not sure anymore. But yeah, these are called Higman, Neumann, Neumann extensions or HNN extensions in short. I think originally they use these kinds of groups constructions to prove that any group, any finitely generated group embeds in a two generated group or something like this, something crazy like this. Any finitely presented group embeds in a two generated group. And you can prove it using HNN extensions. Yeah. Okay. So these are examples of graphs of groups. And the main theorem is of Serre, of trees by Serre, is that if G acts without inversions on a tree, if you look at the graph of group given by quotienting by G, graph of groups given by quotienting X by G, pick any tree. So first of all, the graph of groups does not depend on the choice of tree. You have to prove that. It's okay, it's not too hard. Does not depend on the choice of the maximal tree. So you look at the graph of groups. So this is like saying fundamental group does not depend on the base point. Right? So you look at the quotient graph of groups, you look at the fundamental group based at any tree, any maximal tree, and that will be isomorphic to G. We have seen it for this example, of course, right? The graph of groups is the amalgam, right? If you have a quotient and if you have a quotient which looks like this is the fundamental domain, right? Graph of groups is this amalgam, and the amalgam is isomorphic to the original group that it was acting, that was acting on the tree. So in general, this is true. If in the case that you don't have a segment as fundamental domain, you don't even have a fundamental domain, let's say, you just know the quotient, you can recover the full group back from all the stabilizer information of the quotient. And well, the proof is again 2 lines if you know algebraic topology. But yeah, so the proof is, I mean, I don't know how many people actually are, I mean, let me see if anyone knows here knows algebraic topology here. Yeah, okay, so there's at least one person who knows algebraic topology. So let me just briefly say that if you have a graph of if you have the quotient graph of groups, so X quotient G, then you can so then you can take the stabilizer, vertex stabilizers and edge stabilizers, and then take B of everything, right? You take classifying space of everything, and then take a co-limit, yeah, like I described earlier. You fatten everything up. So basically, you have this and fatten everything up. Then what does the universal? Okay, no, I shouldn't say it like that. Maybe I should say it like, yeah, okay. So let's start with the tree. Okay, let's go backwards. Let's start with the tree. So you have group acting on a tree. Yeah, you have a tree here. Now the problem is that there are vertices which are fixed by G, fixed by some parts of G, right? There are stabilizers for each vertex, stabilizers for each edge. You can resolve all these stabilizers by fattening things up. You can fatten each of these vertex groups. You can fatten each of these vertices to the to E of that stabilizer, right? So for example, suppose this is a vertex V and the stabilizer is GV. Fatten this up to EGV. This is only for people who know algebraic topology. Then GV is acting on freely on EGV, right? Because that's how you characterize E of something. So fatten each of these edges also to EGE, yeah. Then after fattening everything up, G now acts freely because originally GV was fixing this, but now once you fatten everything, it goes la 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 la, and it acts freely here, right? EGV by GV is BGV. There is a free action here. It just goes around and around. So the quotient after you do that, the quotient is exactly X X double quotient G. I mean this the graph of groups. I mean the B of this graph of groups. So if you what you get is exactly the underlying graph is X by G, and every vertex is replaced by BGV for every V in vertex space, and every edge is replaced by BGE. Okay. All right. So, and the fundamental group of that is exactly the fundamental group of the graph of groups. So that's the proof using algebraic topology. But also you can do it elementarily. So what Serre does, I think, is, yeah, so let's see if I can make some space. Yeah, I'll just delete it because we have done this example. So what Serre does is he uses the method of divisage. So what he does is he boils down everything to these two cases. And how do you do that? Well, roughly speaking, suppose you have a quotient which looks like, yeah, suppose, take some simple example. Suppose you have a quotient which looks like this, yeah. Then you partition the vertices to consist of single vertex here and a single vertex there. Then when you look at the tree, you have partitioned the vertices of the tree into these two colors, right? Green colored vertices and blue colored vertices. And now collapse each green color, each subgraph which is colored green to one point. Then again you're boiling down to this case, right? You have a bipartite tree on which G acts. So it has to be a free product of amalgamated free product of the green part of whatever group you get out of the green part and whatever group you get out of the blue part. So now you can induct and then break it down to just bunch of graphs of this sort or this sort. That's method of devisage. Anyhow, so now that's I hopefully have, even though I haven't given a complete proof, I've been able to convince you that this is in fact true. This theorem is in fact true. So let me say some corollaries of this theorem. One is that it completely understand. I mean, using this theorem, you can completely understand all the subgroups subgroups of amalgamated free products. So suppose that gamma is a subgroup of G, which is the amalgamated free product of G1 and G2 along a subgroup, such that gamma is not entirely contained in, not entire, that's not what I mean. Such that gamma is not gamma intersects every conjugate of each of these factors trivially. Okay. Then I claim that gamma is free. Well, why is this true? Since gamma does not intersect any of these conjugates, it must, so G acts on this tree, right? So we have discussed this before. So G is equal to G1 star G2 along A implies that G acts on a tree without inversions, such that fundamental domain is AQ. Yeah. And this action restricts to gamma. Yeah. So gamma also acts without inversions on this tree. And since gamma does not intersects trivially every conjugate of G1 and G2, that means that it has no stabilizers. Yeah. So there are no vertex stabilizers, and no vertex stabilizers also mean no edge stabilizers, because edge stabilizers are just intersection of the vertex stabilizers. So this action is free. That means gamma is a tree. We have proved that last lecture. Okay. So every subgroup of amalgamated products which do not intersect, which intersects each of the conjugates of the factors trivially, is in fact a free group. So amalgamated free products contain many free groups in general, typically. Yeah. And okay, so you can ramp it up a little bit. A subgroup of a group is called bounded if it's bounded in the word metric. So word lengths are of bounded size. Yeah. So my claim is, if you have a bounded subgroup of amalgamated free product, then some conjugate has to be contained in one of the stabilizers. And why is this true? Well, okay, let's try to prove it. So up until now, everything is clear, right? So this theorem is clear, yeah? Maybe someone can verify if it's clear or not. Is there any question? You can ask me, because we're doing quite fine on this, on the speed. All right. So let me say why this is true. This second fact is true. So let me insert a page. Yeah. So why is this true? So again, G acts, so since G is an amalgamated product, G acts on freely on, G acts without inversions on a graph, on a tree X. And gamma is a bounded subgroup. So gamma action also restricts to gamma, yeah. And gamma is a bounded subgroup. So that means that there exists a point P such that, not there exists, for any point P actually. So that means that if you fix a point P, so if you fix a point P in the as a vertex, then the orbit of the point is bounded in the tree. Right? Because word lengths are bounded. So the orbit has to be a bounded subtree. So the tree looks like this. The orbit of a point P here has to be some bounded part of it. So in fact, the gamma action restricts to, yeah, 1 second. Yeah, so gamma action restricts to a bounded subtree of X. Okay. But now, yeah, is there any question? All right, if not, then. So the point is this bounded subtree is, so it's a finite subtree, right? So it's a finite tree. So if it's a finite tree, it has leaves. Fix any leaf, any point in the leaf and look at its orbit. The whole orbit is contained in this bounded subtree because the bounded subtree is literally an orbit. Then throw away that orbit. Yeah. So then iteratively you can shrink this bounded subtree. Yeah. So you can just pick a point here. So you have this bounded tree here. You can pick a point as a leaf and then throw away the orbit of the leaf. So now the tree is smaller. So now gamma acts on an even smaller tree. And you can iteratively throw out these leaves so that these bounded subtrees are smaller and smaller and smaller. And so what can it be at the end? It has to be a point, right? So gamma basically has to fix a point. Fixes a point. Right? Any action of a group on a finite tree has to have a fixed point. That's what I've proved, really. And so this proves that some conjugate of gamma is contained in either G1 or G2 because it fixes a point. All right, so let's do property FA now, which is really about these kind of fixed point results. So Serre's property FA is that if a group is said to have Serre's property FA, if for all trees, if you have a group acting without inversions on the tree, then there exists a fixed point. So any action on the tree has to have a fixed point. And the theorem is the following. If you have a countable group, then having property FA is equivalent to having these three properties. 1, G is not an amalgam. 2, Z is not a G quotient. And 3, G is finitely inherited. All right. So of course, this will require some space. Yeah, I have some space here. Fine. Let's do this direction because it's easier. Yeah, so okay, so maybe someone can tell me the answer. So if G has property FA, can one of you tell me if it's clear that G is not an amalgam? How should I start even thinking about it? Just feel free to say something. You don't have to be correct.
So, did we have that if G was an amalgam, then
Yes.
G acts freely on a tree, right?
Not freely. G acts
Oh,
on
yes, only
with
acts.
fundamental domain 2 edges. Yeah, correct. It
Oh,
acts
okay.
with the fundamental domain being an edge. Yeah.
Yeah. Okay, never mind. I
Yeah.
absolutely right.
No, but that's correct. That's correct. That's a good way of thinking about it. So suppose that G has FA and G is in fact an amalgam. We'll come to a contradiction, right? So if it's an amalgam, then it acts on a tree. But it doesn't act freely, but does it act, or, I mean, does it have a fixed point?
It shouldn't, but uh,
So what do I mean by it is an amalgam? I mean, it's of the form G1 star A G2. But of course, then every group is an amalgam, right? Because G1, G2 can be an identity. So when I say it's an amalgam, I mean that it's an amalgamated product, but G1, G2 are non-trivial. Stabilizers of each vertex are exactly G1 and G2, right? When I act on that tree, when I get from amalgam to the tree, stabilizer of each vertex is either G1 or G2 because the fundamental domain is this, right?
oh yes, yes, yes.
And every vertex, yeah. So, and G1 and G2 are not for the full thing. So there are no fixed points of the action. So it is not free, but indeed there are no fixed points. So that was correct. All right. Excellent. So, and why does property FA imply that Z is not a G quotient? Well, this is slightly trickier. Let's see. Sorry, I haven't prepared at all, so I'm thinking about it as we go along. So G has FA implies Z is not a G quotient. Why is that true? Suppose Z is a G quotient, yeah. Then, So then G acts by translations on this guy, right? Okay, let me go to the next page. So this one is proved. So 2, G acts by translations on Z, right? Because G acts, so Z is a G quotient. So suppose that G by N is equal to Z. Then G acts on the Cayley graph of G by N, right? With some generalities, I don't care. And that's really Z. But this is a tree, right? This is a tree. This is a tree on, this is a 2-valent tree. And it acts by translation, so it has no fixed points. That was simple. And 3 is that G is finitely generated, right? That was 3. G is finitely generated. So why is this true again? Well, the point is, yeah, you can again suppose not, okay. Let's see. So, yeah. So the point is G is countable. I think that's the point. So G is countable. So G you can write as, it's a union of, increasing union of finite groups, right? Because G is countable. G countable implies that it's an increasing union of finitely generated groups, not finite groups, finitely generated groups. So it's an increasing union of finitely generated groups. Gi finitely generated. Okay. And now we can form a graph which is vertices are the cosets. Yeah. So consider a graph whose vertices are all these cosets. Yeah, it's a shattering trait. Okay. So you have all these cosets are vertices of this graph, and the edges are exactly, there are edges whenever, I mean, whenever it's something in G by G, something is in G by Gi is also in G by Gi plus 1. Yeah. So edges are, the edge sets are, yeah. Yeah, so they are of the form A, B, and BA, such that A is in G by Gi and B is in G by Gi plus 1. Right? So whenever something is in G by Gi and something is in G by Gi plus 1, I join them. And on this graph, G acts. So G clearly acts on this graph. All right. So it has to have fixed point. So therefore it has to have fixed point because we have property Fa. So there exists fixed point. But that means that, yeah, so if there is a fixed point, then some coset is fixed under the action of G, some coset G by Gi, right? So let's say that there is a fixed point, the fixed point is G by Gn and some coset of Gn. So let's say that coset is GGN, so GGN. So this is fixed under the action of G, but that forces Gn to be equal to G, right? How else can a coset be fixed? So one of these Gn is G. So that means G is finitely generated. Okay, so for the converse, so we proved one direction. For the other direction, it's slightly harder. So for the converse, so we have a group which has no Z quotient, which is finitely generated, and it is not an amalgam. We want to prove that it has property Fa. So let's say that G acts on a graph, yeah, acts on a tree rather. So G acts on a tree without inversions. Now you look at X by G. We know from the fundamental theorem that we mentioned earlier that fundamental group of this graph of groups at a tree, but I'm not writing the tree because the tree is not that important, is isomorphic to G, right? Fundamental group of the graph of groups is isomorphic to G. Okay, so I need some algebraic topology again, but yeah, the point is now the fundamental group of the actual fundamental group of the quotient graph. So X by G is a graph, right? It's also a graph. The actual fundamental group of the quotient of the quotient graph is a quotient of the flattened fundamental group, right? Because X by G is some flattened thing. So if the underlying X by G looks like this, then X double G. So the fundamental group of X double G is obtained from the fundamental group of this complex, which is given by taking the mapping cylinder construction of everything. It's a flattened object, yeah. And so if you collapse everything, collapse all the fatness of the vertices and the edges, then you get back the underlying graph. So the fundamental group of X by G should be a quotient to the fundamental group of X double quotient G, and that is indeed the case. So if you quotient by all the stabilizers of G by subgroup generated by all the stabilizers and of the edges and the vertices. GV union G, yeah, GV union G. Then that's isomorphic to the fundamental group of the quotient. Okay. But pi1 of X by G is a free group because X by G is homotopy equivalent to a union of circles, right? Fundamental group of any graph is a free group. So it has a Z quotient. So G has a Z quotient. That's impossible. Unless this is simply connected. X by G is simply connected. Unless X by G is simply connected. So it's in fact a tree. Is a tree. So the quotient has to be a tree. Because G has all those hypotheses there. Z is not a G quotient. So quotient has to be a tree. But quotient is a tree implies that what does it imply exactly? Yeah. So quotient is a tree implies that so X double G is a graph of groups on a tree. On a tree. So the quotient looks like a tree. and to each vertex you have some stabilizer associated to it, and to each edge you have some stabilizer. And the fundamental group of this graph of groups will be an amalgamated product of everything, right? So in particular, it will be an amalgamated product of this part and this part along this edge G. But fundamental group of the graph of groups is exactly G. So G is an amalgamated product, but G cannot be an amalgamated product because that's a hypothesis, right? That's one of these hypotheses. Part one. So that implies that I mean, it cannot be a non-trivial amalgamated product. So that implies that it has to have a fixed point. I mean, so one of these has to be the whole group. And then you look at the other one and induct to get to a vertex, which is a fixed point. So if this was a fixed point, for example, then we'd be done because I have a group acting on a graph and I have a fixed point. So that's property FA. Okay. So I hope that was clear. I mean, you need some algebraic topology somewhere to argue, but if you look at Serre, then he also uses somewhere he uses an algebraic topology to, I mean, get away with something. But I mean, you cannot argue without some kind of pi1 argument. Okay. So that's that. So we have proved that property FA, if and only if these properties hold. So now, what do I want to say? Yeah. So groups with property FA. So what are the properties of such groups? Okay, so the first thing is that finitely generated torsion groups are always have property FA. And why is this true? One second, let me remember. Yeah, why is this true? Yeah, I see. So the point is, yeah, so suppose that, okay, so suppose G is a finite, so okay, let's see, let's prove it. So suppose G is a finitely generated torsion group. So certainly 2 and 3 holds. It is finitely generated and it has no Z quotient because it's torsion. It's completely torsion. Every element is torsion. It cannot have a Z quotient. So we have to prove that it's not an amalgam, right? So suppose it is an amalgam. So suppose that G is isomorphic to G1 star G2 along A. G1, G2 non-trivial groups. But then look at an element S here and look at an element T here, yeah. Element of G1, element of G2. Then ST is never torsion. Because suppose it is torsion, then ST, so on and so forth, ST equal to 1, right? After some time, ST to the power of n equal to 1 for some n. But this is a word which is of the form we discussed, right? It is a word such that no consecutive pair of elements in the word belong to the same group. Such a word cannot be trivial in a amalgamated free product. So finitely generated torsion groups are indeed groups with property FA. Okay. Second thing is a group has property FA implies that the quotient has property FA. Why is this true? Yeah, that is because, yeah, so maybe someone can say it. Is this clear to you why this true? Group has property FA implies the quotient has property FA. Remember that property FA means that if group acts on a graph, acts on a tree, then it has a fixed point. Can someone tell me why this is true?
Just a guess. So let G act on the Cayley graph, and G mod n act on the Cayley
Let G act on the very good start.
graph of, and G mod n. So we
Yeah.
know that. So this means this has a fixed point, and we have to show that this also has a fixed point. So Cayley graph of G mod n, comma.
Well, we
of
don't.
some
So
z.
no. So 1 second. So the Cayley graph need not be free, right? The Cayley graph need not be a tree, right? Because the groups need not be free.
Yes, yeah.
Yeah. So the Cayley graph doesn't quite work. But you're saying that let G mod n act on some graph, yeah? Let G mod n act on some tree.
Yeah.
So what do we know? We know that it has to have a fixed point, right? And then
No, we have to prove that.
no, we have to prove that it has to
We
have
have to prove this. Yeah, exactly. So we know that G
Yeah,
also,
okay, yeah.
if G also acts on this X tree, then it has a
Yes,
fixed
so
point.
the point is exactly G acts also acts on X. It has a fixed
And
point.
we know it
And that
has a
fixed point
fixed
also has to
point
be a fixed
that,
point of G mod n, right?
yeah.
Yeah, so G acts on X. So G mod n acts on X implies G acts on X. So it has to have a fixed point. So there exists an X such that Gx equal to X for all G in G. But that means Gn X equal to yeah, so right quotient. Which direction the action should be? Yeah, so something to verify here. 1 second. So let me write it precisely. But you are right. So G mod n acts on X implies G acts on X. And so that means that means there exists a fixed point. So that means there exists X such that Xg equal to X. So I'm acting on the right for all X in X. But that means Xgn equal to X for all G, sorry. For all G in G. For all Gn in G by n. And that is exactly property T for property Fa for G by n, right? G by n acts on X implies it has a fixed point. Right, so that's the proof. So every quotient, the property Fa goes through quotients. Okay, what about subgroups? Property Fa does not go through subgroups. It does not even go through finite index subgroups, but I'll come to that later. So if G prime has a finite index in G, can you prove that G prime has property Fa implies G has property Fa? Well, I don't know. Maybe I can't even prove. 1 second. I have forgotten how to prove this. So G prime is finite index subgroup of G. G prime has property Fa. So the smaller thing has property Fa implies the bigger thing has property Fa. Why is this true? So let's see, X be a tree and G act on X. So this action restricts to G prime. So G prime acts on X. And this has to have some fixed point, right? So for this, there exists some fixed point. For this action, there exists some fixed point. In fact, you can look at the tree, you can look at the subgraph of X, which is fixed by G prime, pointwise. That has to be a tree, right? There's a tree in X. And then the G action restricts to Xg prime. Yes? No, not quite. 1 second. Okay. So assume that G prime is normal. So first assume G prime is normal. So assume G prime normal here. Just assume it for some time. Then I can look at G by G prime, and this acts on Xg prime. G by G prime now acts on Xg prime, the graph which is fixed pointwise by G prime. And this has to have a fixed point. Why? If this is a fixed point, we're done. because then we get a fixed point of G as well, because something which is fixed by G prime and then it is fixed on top of that by G prime is fixed by G. So why does G by G prime fix something in X G prime? Oh, because G by G prime is finite. Yeah, because finite index, G by G prime is finite. It's a finite group. Finite group which acts on a graph has to have a fixed point. This is essentially the same argument as before. Same argument as this thing. Here the tree was finite. But of course, if you have a finite group, then orbits of any point has, any point has finitely many orbits. So you can look at the, so you can now shrink the, so now, you can look at a tree which is invariant under, you can look at a tree which is invariant under the action of the finite group, because you can look at the tree and you can look at the orbit of the tree. And then you can keep deleting points. So if you have a finite group acting on a tree, it has to have a fixed point. So G by G prime is finite, implies it has a fixed point. G fixes something in X G prime. So that means G fixes that point, because it's fixed by both G by G prime and G prime. And now why can we forget about this normality hypothesis? So this should be known to a first year. We assumed here G prime is normal. Can you do it without assuming G prime is normal? Anyone? Well, the point is that if you have a finite index subgroup of a group, then you can get a finite index normal subgroup of the group, which is contained in the subgroup. Okay. If you have finite index subgroup of a group, then you take all the intersections of all the conjugates of the subgroup, and there will be only finitely many, because there's finite many cosets. And if you look at the intersection of all those conjugates, you get something which is normal and contained in your subgroup and finite index. So you're done. You can always boil down questions about finite index subgroups to finite index normal subgroups. But this is not true. If you have G which has property Fa and G prime in G has finite index, then G prime need not have property Fa. Okay. So let's see, I think I only have 15 minutes left. So what do I want to do? Let's see. Yeah, we could talk about this. I mean, why SL3Z has property Fa. Yeah, so I need to build some machinery for that. Let's see. Let me do it quickly. So yeah, so let me give an example of this guy, because this will be useful. Yeah, so the example I think is that you take A, B, C, A to the power of P equal to B to the power of Q equal to C to the power of R equal to 1, A, B, C equal to 1. This is called triangle group, if I recall correctly. Triangle group, or the oriented triangle group, Von Dyke subgroup of the triangle group. Yeah, triangle group. Yeah. Okay. So why does this have property Fa? Yeah. So the point is, if you have this group, so let's call it delta. Yeah. Just forget about PQR. Just call it delta. Delta let it act on some tree. Then A, B, C are finite order. So A, B, C fix points on X respectively because they are finite order automorphisms of the tree. Remember from our earlier, yeah, so this is also another proof that finite groups will always have fixed points when you act on a tree. We proved earlier that there is a classification of automorphisms on the tree, those which are hyperbolic and those which are elliptic. And elliptic ones fix some point and kind of rotate it around it. And the hyperbolic ones were just translations along some geodesic by infinite geodesic. Now, if you have some finite order automorphism, it cannot translate along a by infinite geodesic because that clearly has infinite order. So it has to be an elliptic automorphism. So if it's elliptic, it fixes points. So A, B, C are both all finite order automorphisms of the tree when you act on it on the tree.
Can
so
you
they are all yeah, sure. So the point is, if you have automorphism of a tree, they are either hyperbolic or they are elliptic, yeah. And hyperbolic ones are always translates along some bi-infinite geodesic. So they are clearly finite or infinite order. So the finite order ones has to be elliptic, which
okay,
fix points.
and
We
which
proved
fixes
that,
a point in the interior,
right?
right? Okay.
Yes, in the interior, not on the end. Yeah. So A, B, C all fix points on X, but may not be the same points, right? They can be different points. If they fix the same points, we're done because the group is generated by A, B, C. So how do you prove that there is a common fixed point? Okay, so this is kind of a geometric argument. Let's see. So you have this tree. Look at the set of points fixed by A. That's a subtree. I mean, need not be bounded. Subtree. I don't like this picture of a tree. Let me draw it properly. So this is the tree, yeah. Tree should look hyperbolic. And you have, you look at fixed points of A. So this is everything which is fixed by A. And suppose that, what do I suppose? One sec. Yeah. So one second, getting confused. Yeah. So suppose look at the fixed points of B. Yeah. So they need not intersect. I mean X. So a priori they need not intersect at all. But I'll prove they intersect. They intersect because essentially because AB, I mean C has another fixed. So C has a fixed point. C equal to AB here. Note that C equal to AB inverse rather. So A is the automorphism of the tree, B is the automorphism of the tree, and XA and XB, suppose they are disjoint. So then there is a path, geodesic of least length, which is bigger than 0, joining XA and XB. Now, so the picture looks like this. This is XA, this is XB. This is point P, this is point Q, let's say. Q is not fixed by A, right? Because this whole path is going outside XA. It only intersects XA at P. Because otherwise you can shorten it. It's the least length geodesic, joining XA and XB. So act on the whole path by A. Then Q goes somewhere here. And the whole path goes somewhere here, right? So AQ. Now the point is BQ equal to Q. B is fixed by Q. Q is fixed by B. So BQ equal to Q. So ABQ equal to AQ. Right? Yeah. ABQ equal to AQ. But AB is an automorphism. So AB takes Q to AQ, yeah? So AB takes Q to AQ. But AB is an automorphism which also has fixed points because AB is literally C inverse and C is finite order. So AB is finite order. So AB also has a fixed point. So AB is also rotation about a point, right? It fixes some point and rotates about it. And what point can it fix? It takes Q to AQ. So the point it fixes has to be the midpoint of this geodesic, right? Joining Q and AQ. The geodesic joining Q and AQ is exactly this geodesic, Q to P to AQ. Because there is only there's unique geodesic between 2 points in a tree. And if you have the automorphism of finite order taking one point to another point, then the fixed point has to be the midpoint of the geodesic joining those 2 points, right? Because it kind of rotates about this point. Well, you can prove it also explicitly. Suppose that there is a point P, okay, and then suppose it takes this point to sigma P. Then you join P to the, then you look at the least length geodesic joining P and the fixed point set of the unique fixed point of, or the fixed point set of the automorphism. And then the geodesic between this point and sigma P is just sigma translate of this geodesic gamma. And these are the same lengths. Gamma and sigma gamma have the same length. So the fixed point is in the middle. The midpoint is a fixed point. So similarly here, the midpoint of Q and AQ has to be the fixed point of AB. So AB must fix P. Okay, but this cannot be right? Why is this not right? One sec. Yeah. So then you multiply by A inverse both sides. BP equal to A inverse P. But P is fixed by A, so P also has to be fixed by A inverse. Okay. This is P. So P is fixed by B. So therefore P is in XP. But that is impossible because I mean they were some distance apart, right? So XA and XB has to intersect. There is a common fixed point of A and B. But similarly there's similarly B and so yeah, if it has a common fixed point, then C it's a common fixed point of C also, right? Because A fixes it, B fixes it, AB fixes it. So that fixed point, I mean, is a fixed point of this group. Okay. So that means this triangle group is in fact has property FA. But if 1 by P plus 1 by Q plus 1 by R is less than 1, then these kind of triangle groups are what are called hyperbolic triangle groups, and they have many subgroups which do not have property FA. In particular, they have fundamental groups of surfaces as subgroups, and they do not at all have property FA. I mean, they contain free groups. These guys contain free groups. I mean, not contains free group, but contains group which have quotients free groups. Yeah. So so what I mean is these guys contain fundamental groups of surfaces, and fundamental groups of surfaces are do not have property FA because you can quotient and get Z. They will have free quotients. So no way in hell can these have property FA. So yeah, property FA does not go through quotients. Okay. So I wanted to say something about SL3.
That PQR in the triangle group, so does it somehow relate to like how much like distortion there is in like somehow because of ABC equal to 1, so like somehow do they correspond to the angles, like is there some relation with them?
Exactly. They correspond to the angle. No, you're absolutely right. They correspond to the angle. So if you look at okay. So I'm running out of time anyways. I'm probably not going to be able to talk about SL3Z, but I can say something here. There's no point hijacking someone's Zoom, right? You'll probably have work with it. So I have. So take the hyperbolic space. Take a triangle with angles alpha, beta, gamma. Yeah. So you in general know alpha plus beta plus gamma is less than pi. The point is you can also you can also realize any triangle which is of the form pi by p plus pi by q plus pi by r, where 1 by p plus 1 by, so yeah, let's see. You can realize any triangle which is of the form pi by p by pi by p, pi by q, pi by r, such that 1 by p plus 1 by q plus 1 by r is less than 1. You can realize such triangles in the hyperbolic space. This is an exercise in hyperbolic geometry. You can do it. It's not hard. You just have to do apply what is it called? Intermediate value theorem, intermediate value property. Yeah, intermediate value theorem. You have to apply intermediate value theorem. You fix 2 points and then bring a point to from infinity to some finite point. At infinity, all these angles are, I mean, they're 90 degrees. So you can kind of slide the point closer and closer, and you see that all the angles are realized. No big
Yeah,
deal.
got it.
So you can realize it as a triangle. And now look at now look at the group generated by, so these triangles, I mean, sides extend, right? These sides extend the sides, and consider alpha to be reflection about this side, beta to be reflection about this side, gamma to be reflection about this side. So alpha, beta, gamma, they generate a group. Okay, and this alpha square equal to 1, beta square equal to 1, gamma square equal to 1. But alpha beta, what is alpha beta? If you compose two reflections, you get rotation, right? Alpha
So
beta
it
to the
will
power
be
of
a reflection like
alpha.
opposite of to the side, like corresponding to gamma. Oh, okay.
Right. Yeah, yeah,
Sense.
you're
Okay,
exactly
got
right.
it, got it.
Exactly right. So inside this, as a index 2 subgroup is contained is delta. I mean, what is contained is delta as an index 2 subgroup. So it is a reflection group. I mean, it's subgroup of a reflection group. It's called a Van Dyke subgroup of a Coxeter group. Coxeter groups are reflection groups. You take some arrangement of lines and then look at all reflections along these lines and generate a group out of that. So this is the Coxeter group, hyperbolic Coxeter group, and inside it is contained the Van Dyke group. And yeah, so that is the relation with hyperbolic geometry. And these groups are all hyperbolic. I mean, if you have read some hyperbolic geometry, these groups are all hyperbolic, Roma hyperbolic in the correct sense of the word. Yeah, so I don't know if I probably shouldn't take more time and explain why SL3Z is.
I guess we have time because there is no meeting after this, and this meeting like won't end at 3:45 or whatever the time limit
Oh,
is.
so there is no meeting after this. You're sure about that?
Yeah.
Oh, that's
Because
excellent.
it's
So
Sunday, right? So
okay, yeah, okay, yeah. I'm okay. So I'm always, I mean, hesitant to kind of, because this one is also the class Zoom, right? I mean,
yes.
yeah. Okay. Anyway, so yeah, maybe I can talk about SL3Z if you want. So should I say something or no?
Yeah. We have time, right? Can you like cover it in 15 to 20 minutes, right?
Yeah, sure. Yeah, sure. It
Yeah. So
should take
that's
10
great.
minutes.
Yeah, great. We have that much time.
Okay, so yeah, okay, so I can say why SL3Z has property FA. Okay. So the main thing is that SL3Z has property FA, yeah. Has property FA. So let's see. So in particular, it is not an amalgam. So you have an example of a group which is not an amalgam. Explicit example of a matrix group. And property. So I haven't explained this, but property FA is related very closely to what is known as property T. So I have written something here. Hasdan's property T, which is I mean, you can write books about this property. I don't know much, but one of the definitions I find is sort of easy to understand is if H is a real Hilbert space and G is a group which acts on H. So G need not be a discrete group here. G is a group which acts on H by affine isometries, then it has a fixed point. So it is exactly like something like trees, right? The property FA we saw. And so there is a theorem which is that if G is a countable group, then G has FA implies G has property T. Okay. But the converse is not true because property T goes through for subgroups, finite index subgroups, but property FA does not, as we saw earlier. And these kind of theorems are by Margulis. You have matrix group of higher rank, so they have property T, and property T for goes through between so if you have a matrix group so if a matrix Lie group which has property T, then any lattice will have property T as well. I think that's by Margulis. I'm not sure, but I'll prove that there's property FA. That's the least thing I can do. Okay. Let's see. Okay. One sec. Yeah, so I need some lemmas. So one lemma we have already proved is that if AB are, so if G is a group acting on X, so let's see, G is a group acting on X and G is generated by S1 or Sn, each Si has a fixed point. Then each Si has a fixed point and Si Sj also has a fixed point. So all the elements and their products and their mutual products have a fixed point. Then G has a fixed point. We saw it for 2 elements, but for many elements, why is it true? Well, you just use induction. We saw it for 2 elements, and suppose you have another element. Okay, so yeah, that's really it. I mean, just easy. This is easy. But just boil it down to 2 elements. It's easy. I mean, you just take products and then see what happens. You can take it as an exercise as well. Just do it. Just knowing it for 2 elements, you can take it as an exercise. I need another lemma, which is yeah, something about nilpotent groups, right? Okay, so suppose G is FG nilpotent. Suppose finitely nilpotent group. Is there anyone here who does not know the definition of nilpotent? Then I can recall. Just let me know because it's easy. Then either A or B, mutually exclusive. Either G has a fixed point, or there exists bi-infinite geodesic along which G translates. Okay. So either G is completely elliptic. So if you have finitely nilpotent group acting on a tree without inversions, then either G is completely elliptic. So every element is elliptic with a common fixed point. I mean, that has to be true if it's generated by something which is common. Yeah, if every element has as a fixed point, then in particular this lemma kicks in that says that there's a common fixed point. Or G is completely hyperbolic. So it's just every element is translating along a fixed bi-infinite geodesic. Okay, so why is this true? So these two are clearly mutually exclusive because if suppose B holds for some element, not some element, but suppose B holds, then every element is hyperbolic. I mean, this is obvious. I mean, because hyperbolic elements cannot be elliptic. So they are clearly mutually exclusive. And So why is this true? Why is it true that one of these hold? The point is, what does nilpotent mean? Nilpotent means that there exists a composition series such that the quotients are cyclic. So there exists a sequence of subgroups. This is the definition of nilpotent, by the way. So if you don't know the definition, this is, I hope I'm able to explain what is the definition. So this is, so G is nilpotent implies there exists a sequence of subgroups such that G0 is normal in G1, G1 is normal in G2, Gn minus 1 is normal in Gn. Put normal signs here. Such that Gi by Gi plus 1, other way around, is cyclic. This is stronger than solvable. Solvable says that Gi plus 1 by Gi are abelian. Okay. So suppose this holds. So suppose this is definition of nilpotent. Yeah. So let's see. Yes, the point is, I mean, suppose, okay, so we'll assume by induction that it is the theorem is true for all nilpotent groups of length n minus 1, where length, by length I mean the length of the composition series. So in particular, it is true for Gn minus 1. So Gn minus, so if you have so Gn minus 1 has a fixed point. So the action on X restricts to Gn minus 1 has a fixed point. And now you pass to this quotient Gn over Gn minus 1. This quotient acts on X Gn minus 1 like earlier. And this is a cyclic group. So since it's a cyclic group, it has to be completely elliptic, right? It just has to be rotations about a fixed point. So has a fixed point. This follows from our lemma earlier, because everything is, it's one generated. Of course, it's generated by something, so it has to be elliptic, and so all powers has to be elliptic as well. This is a finite cyclic group. Yeah, did I? Okay. Oh, so this quotient need not be finite cyclic. So either it's finite cyclic. If it's finite, then yeah. Okay, so how do I say that? 1 second. So okay, so there is something that you should say. If it's finite, then it has a fixed point. That's the point. Yeah, so I should say it like this. Maybe I should organize the proof like this. So true for Gn minus 1. So that means either A, Gn minus 1 has a fixed point, or B, Gn minus 1 is a translates along a bi-infinite geodesic. If this holds, then you look at this quotient. Then by earlier argument, Gn by G, so G by Gn minus 1, G by Gn minus 1 acts on X Gn minus 1. Okay. So it's a cyclic group which acts on this guy. But then it should have a fixed point. So why is that true? Because 1 second. So if it's finite cyclic, we're done, right? If it's finite cyclic, we can it fixes a point. But if it's infinite cyclic, it can translate along a geodesic. That's what I'm worried about a little bit. 1 second. Yeah, sorry, I'm getting confused. Why is this true? Yeah, maybe the point is that it doesn't matter anyway, because I mean, if you have something which is, so if it acts by, I mean, if it, yeah, so if it acts by hmm. Yeah, I'm getting confused. Do any of you see it? By the way, if any of you see it, you should just say it. Why this is true? Because I'm getting because Z can act with translations, right? So G by G n minus 1 can be Z, and it acts by translations. So I don't see the contradiction there. But it acts by translations on the set of fixed points of Gn minus 1.
Maybe you can add a reference right now since we are running out of time, and let's.
Yeah, sure. So okay, so yeah, maybe we should discuss this later and why this is exactly true, because yeah, it should be true by because something like this, right? I mean, because if all the factors are finite cyclic, then there is no problem. It has to be acting by rotations. All the quotients are acting by rotations, are elliptic rather. But if one of if whenever you have some cyclic quotient, Z is infinite cyclic quotient, then it can act by translations along a geodesy. So if whenever that happens, then the whole group will start acting by translations. That's the point. But yeah, I'm not able to gather myself and say why exactly this is true here. Let me apply this to prove that SL3Z is in fact has property FA. So the point is SL3Z is generated by all the shearings, right? So SL3Z is generated by all the shears. So yeah, so denote Eij to be the matrix which is delta Ij. Yeah. On the ij spot, it is a 1 and everything else is 0. Now look at the matrices 1 plus Eij. 1 by 1, I mean identity matrix. Yeah. I plus Eij. These generate SL3Z. These are all the shears. Shears generate SL3Z. So yeah, so Serre draw the nice picture. So let me draw it here. So I plus E11, I plus E12. Not 1, 1. Okay, I can chuck those out. Yeah, not 1, 1 because Ij distinct generated by these because those are not even rank, those are rank 1. I plus E13. Yeah. Okay. So these matrices generate SL3Z. And the point is the commutator, these two commute. So if you take alternate matrices, these commute. Just check it directly. Yeah. So if any alternate pair of matrices will commute. I hope that's true. Yeah. So 1 second, let me just check it quickly. 1 2 1 3 3 2 2 1 3 2. Yeah, okay, this is correct. This is correct. Okay. So any alternate pair of matrices will commute. This will commute with this will commute with this, so on and so forth. Yeah. And the commutator equals the inverse. Commutator of these two will be the inverse. Yeah? These things you can check. So if you take a triangle and take any pair of points and take commutator, this will be the other point of the triangle. And the subgroup generated by these two, of course, this will be there as well. For any subgroup generated by this triangle, this is something called the Heisenberg group. Heisenberg group consists of all matrices of the form 1 1 1. So this is the classical presentation: 1 1 1 ABC. ABC all integers. So this is a subgroup of SL3Z, right? It's called H3Z. This is the Heisenberg group. So any triangle here generates Heisenberg group, which is nilpotent, by the way. Heisenberg group is something like Z cross Z, semi-direct Z. It's a nilpotent group. All the quotients are cyclic. You can just generate it like that. Infinite cyclic quotients here. So you have these generators for the group. And yeah, so all these triangles span nilpotent groups. So the nilpotent groups must act. So if you have a tree X and SL3Z is acting on the tree, all these nilpotent groups are acting on the tree as well. So they must either have fixed points or must translate along some common geodesic. We want to prove it as a fixed point. So it either has a fixed point or translates along some common geodesic. But yeah, so why does it have fixed point? So we're again back to the problem. Why does it have fixed point and not a geodesic along which it translates? Yeah. Oh, I see. This is because yeah, this is because there are no non-trivial Z quotients, right? So I think that is the correct reasoning. Yeah, so yeah, so you can check something. You have to check that SL3Z is in fact SL3Z does not have Z quotients. And if it translated along those geodesics, then you'd get a Z quotient, right? It was acting by automorphism on the infinite path. So you get a map to the automorphism group of the infinite path, which is Z. Right? It would be a subgroup of Z. So the image would be a subgroup of Z, which is Z. Any subgroup of Z is Z. But SL3Z does not have Z quotients. That's the point. Not just SL3Z, you don't need to argue for SL3Z, you can argue for just this nilpotent group, H3Z. H3Z does not have Z quotient. The normal subgroup is the other guy. Z cross Z is the normal subgroup. No, I don't mean the normal subgroup is Z. Yeah, the normal subgroup is Z. Yeah, this is not the normal subgroup. So when you quotient, you don't get Z. Yeah, something like this. So it cannot. So all of these nilpotent groups have fixed points. But if they have fixed point, then I mean these nilpotent groups generate the full group, and their products. I mean their products also have fixed point because their products is just yeah, because their product is yeah, because if you take product of these two things, yeah. Yeah, because the product is containing H3Z. That's really the point. I mean, everything in this triangle is containing H3Z. H3Z fixes some point, so everything there fixes a point. Yeah. So there, I mean, the products of these things are also they also have a fixed point. So yeah, so since each of these nilpotent groups have fixed point, the whole thing must have fixed point by this lemma here. By this lemma. Okay. So yeah, so that's why SL3Z any if you have SL3Z and you act on any tree, it has to have a fixed point. That's the point. So that's it, I think. Yeah. So that's all I wanted to say for now. But if you have questions, you can ask. Also, maybe we can clarify this point. So if someone has ideas, maybe they can explain why this is true. So any questions, comments?
If there are no questions, let's end the talk.
Yeah.
If anyone has any questions, you can just unmute yourself and ask right now.
Yeah, for sure.
Well, okay then. Thank you, Balarka, for the talk. I really enjoyed it. And
Yeah, for sure.
yeah, so this is it for today. This weekend's talk series of the Math Club. We'll meet next weekend for sure. The new speaker and the title will be announced this week itself. Yeah. So thank you, everyone. I'll stop the recording now.